All right, greetings. More homework help from section 5.10. We're starting on number 23 for this one. And um, if you didn't watch the previous video where I went through a little bit more of the definition of how to handle at least type 1 improper integrals, I want to go watch that one because at this point I'm just ready to help with finding antiderivatives because I think if you watch the other video, then that should be really all you need at this point. You're going to rewrite that as a limit and go through all those steps. For this, though, you might have trouble finding the antiderivative. And this is just a substitution problem. If you let u equal the natural log of x, and then du, which is a terrible looking du, is going to be 1 over x dx. And we have that right here. And so this is just the integral of 1 over u cubed du, like this, or the integral of u to the negative 3, which we can just reverse the power rule, and we're going to end up with negative u to the negative 2. We have to divide by that negative 2, and I'm just going to put it out here like this, plus a constant, or just negative 1 over 2 natural log of x, quantity squared plus c. And again, you don't need the plus c when you rewrite or when you find the antiderivative in this problem because you'll have a definite integral that you'll be working with. So, rewrite this as a limit, and then this is from e to t now, and then 1 over x, natural log of x cubed dx, and then go through the rest of the process, and you should be able to work it out. 33 is the next one on our list, and that's integral from 0 to 2 z squared natural log of z. Making sure I copied it correctly. So this is our first, from the examples being asked, our first type 2 improper integral, because we don't have infinite limits of integration. The natural log function, you should remember if you just think about its graph, it looks like this, kind of. It has a vertical asymptote at x equals 0, so this graph is discontinuous at x equals 0, improper with discontinuity at x equals 0. So you're going to rewrite this one as a limit, and you're going to let your variable approach 0 because that's where the discontinuity is. But since 0 is the left-hand endpoint, we're going to have to approach from the right because we want to approach from numbers within the interval. And so make sure on these type you use one-sided limits. Not dx, dz. Let's do a little side work to figure out the antiderivative. It looks like an integration by parts problem to me. That's my first gut reaction here. Yeah, there's no substitution for there, so we're going to lip it. If you're thinking in terms of the acronym lip it, L is the first thing. Natural log function is what the L stands for, and so we're going to put natural log as our expression for u. Again, that's a suggestion. Lipid is a suggestion in the integration by parts. It's not a rule. It doesn't always work out well that way, but it's just more than likely to work out well that way. We'll let z squared dz be the dv. We end up with 1/3 z cubed here, and so when we put this back together, we got our 1/3 z cubed natural log of z minus, and then we're going to integrate. We're going to multiply these together, so the 1/3 stays wherever in front of the integral, and in the integral it doesn't matter. 1 over z times z cubed is z squared, and so you put a z squared in there like this. So 1/3 z cubed natural log of z minus 1/9 z cubed plus a constant, and then you'll just go work the rest of this out. You'll probably have to think about the graph of the natural log function when you go to work out that integral. If you're going to want further help on this particular problem, you're going to have to reach out to me, but I think you should be able to finish it without my assistance. 35 is next. Okay, it says sketch the region and find its area if the area is finite. So this notation here is probably what's confusing most of you. It's called set builder notation. Um, and if you plan on studying mathematics in college, you're going to want to become comfortable with it because it is very, very common, at least past a certain level. About your maybe junior year, you'll start to see it a lot. Um, so the brace, whenever you see a brace like that, it's denoting what we call a set. Just a set is, just think of it as a collection of objects. And you're going to read it like this: S equals the set of all. Okay, that's how you want to phrase it. And then it's the set of all what? Well, things that look like this. Okay, ordered pairs X, Y. And then they put a vertical bar. They don't always have a vertical bar. They might put words. I'll say some words in a moment. They could put a colon. It depends on the author and how they want to notate it. But it's the vertical bar is the set of all. Well, no, this is the set of all, the brace. The set of all ordered pairs X, Y, such that, okay, with these conditions, everything that follows that vertical bar is giving us the conditions that X is going to be less than or equal to 1, and y is going to be between 0 and e to the x, inclusive, okay? So if you think about an xy plane, this is where we're getting this from. Got our xy plane. Shift that over a little bit there. Okay, so the xy plane contains all the points xy. We don't want all the points xy because I don't want if this is well, I'm sorry, if this is x equals 1, I don't want these points over here because x has to be less than or equal to 1. So I know it's got to be x is less than or equal to 1. So it's got to be on this side over here, but then it also has to be under this condition. That y is between 0 and e to the x. So if I sketch e to the x, the e to the x graph is going to look something like this, okay? And let's put x equals 1 in there. That's this, okay? So we want all the points in the plane, x, y coordinates, points in the plane, where the x coordinate is less than or equal to 1, so anything to the left of this line, and the y coordinate is greater than or equal to 0, so above this or on that, and less than or equal to e to the x, so less than or equal to the orange graph right here. So what we're looking for is everything that's in this region here, down below this curve above the x-axis from negative infinity to 1. So what we're trying to find here, we're trying to evaluate the improper integral from negative infinity to 1 of e to the x dx. That's all that we're trying to do. This is, S represents the area, all these points. We're trying to find this area. That's all I'm going to help you with for 35. I've described the region. All you got to do is evaluate that improper integral, and you should be able to do that at this point, okay? Pausing as if we were in class and you were be able to ask me a question. Of course, you can't. 39 is similar. Let's go ahead and set it up really quickly. So it's another set of ordered pairs, set of points in the plane. So it's the set, S is the set of all ordered pairs x, y, and then they're going to restrict, so we're not talking about the entire plane, which of course is unbounded. 0 is less than or equal to x, is less than or, was it less than or equal to or less than? Less than pi over 2. So the x coordinates of these points have to be trapped between 0 and pi over 2, including 0 but not including pi over 2. And the y coordinates are between 0 and secant squared. So what's the graph of secant squared look like? I don't know. Does it? So I don't really want to sketch this. If you could imagine, I would sketch the graph of secant squared. I would take the points between the x-axis and whoops, should be secant squared of x. Take those points, and then I'd restrict the horizontal interval between 0 and pi over 2. So what we're trying to evaluate is the improper integral from 0 to pi over 2 of secant squared x dx. This is what we're trying to evaluate here, okay, this improper integral. The reason why pi over 2 is not included is because secant of pi over 2, remember, secant is 1 over cosine. Cosine of pi over 2 is 0, so we'd get 1 over 0. So secant isn't defined at pi over 2. So this is an improper integral with the discontinuity at x equals pi over 2. Now you can find the antiderivative of secant squared. We know that one. So you're going to rewrite this as a limit. So you're going to let your variable approach pi over 2 from the left this time. I'm sorry, the pi over 2 is the right-hand endpoint. So you're going to let t or b or a or whatever letter you choose to approach pi over 2 from the left, and then evaluate this improper integral. You should be able to handle that now that you know what the picture looks like. Let's see, it was 39, so 43 is next on our list. It says to use the comparison theorem to determine whether the integral is convergent or divergent. So the comparison theorem, remember, is going to require us to build a relationship to compare this improper integral to. We're not going to use the definition. Because well, you're not going to be able to find an antiderivative of this, probably. But they want us to use, it doesn't really matter. They want us to anyways. Let's start with some nonsense. X cubed is equal to x cubed, right? Nobody believes that, but just pretend for a moment that it's true. That means x cubed plus 1 is going to be greater than or equal to x cubed. And then 1 over x cubed plus 1 is going to be less than or equal to 1 over x cubed. These are all true statements, and I got most of what I need in my integrand, except I need an x. Now, if I multiply both sides by x, as long as x is non-negative, then it doesn't affect the direction of the inequality. And x is not non-negative, because x is on the interval from 0 to infinity. Those are the limits of integration, so that's our interval that we're looking at. So x is already non-negative, so I can multiply both sides by x and not destroy the inequality here. So I get x over x cubed, but x over x cubed is 1 over x squared. So we need to look at is it really from 0 to infinity for 43? It is. That is interesting. Okay, so this is from 0 to infinity of 1 over x squared dx. Huh. Okay, I thought in my head I thought we were 99% done once we had that, because we've looked at this, but we're not, because we have to break this up. This is two different problems in it, two different improper integrals. It's got a discontinuity at 0, and it's got the infinite upper limit of integration. Okay, so we know this one over here converges. Okay, we did this one. This is example number 1 in your notes from this section. So we don't have to go back and prove that one. We've already proved it. This one over here, however, we haven't proved what it does, to my recollection. If we did, then I've completely forgot about it. But go ahead and take a look at this improper integral from 0 to 1. There's a discontinuity. Discontinuity at x equals 0, and set that one up and see if that one converges. If this one converges, then both of these two converge, and so the bigger one converges, so then the smaller one will also converge. If this one diverges, then the whole thing diverges and we know nothing. You know what? I'm gonna have to keep this going here, so because if we know nothing, I'm gonna want to give you some further help. And for some reason, I just got a bad feeling about this one. All right, so we get this. So we have -1 over x is our antiderivative, t from t to 1. Limit as t approaches 0 from the right. And so if I plug in 1, we get -1. If I plug in t, I get +1 over t. As t goes to 0, this is going to go off to, from the right, this is going to go off to infinity. So this thing diverges. So this doesn't tell us anything. So all that work seemingly was for nothing. All right, so we have to find something else. Well, I'm going back to make sure I didn't write it down again. All right. I'm gonna have to pause and think about it for a moment. All right, after playing around with this for a few too many minutes, ladies and gentlemen, I think there's a typo here. Um, the relationship doesn't seem to work out in any of the techniques that we're doing. I think they want this to be 1 here. Um, and so if this is 1, then we don't need this part over here. And then we get convergence like the back of the book says it's supposed to. Uh, so we're gonna just let's assume that lower limit integration is 1, and when we get what we want, we don't need any of this stuff over here. Since this converges and we have this relationship by the comparison theorem, this one will converge as well. All right, I'm gonna do one more video for the rest of the problems on the list. Go study.